Sometimes when I find the area under a curve or find a definite integral, I don't really care about an exact answer. I care about an approximation. One way to do that is a Riemann sum. In this video, I'm going to talk about one type of Riemann sum called a right Riemann sum. A Riemann sum is when you take that area you're looking for and you break it up into a bunch of rectangles. You approximate it as a bunch of rectangles. For instance, if I added up the area of all these rectangles, these green rectangles, it's going to be approximately the blue area I'm looking for. It won't be exact. I have to squint a little bit, pretend, this is willing suspension and disbelief, but I'm willing to believe it's at least on the right order of magnitude. My error is probably less than 50% or something. The question is, how tall should I make the rectangles? Right? Maybe it should be here, or maybe because of concavity, it's actually different. For a right Riemann sum, I'm just going to make all the rectangles line up in such a way that their top right corner lies on the function. In other words, the rectangle I use between x equals 0 and x equals 1 will have a height of f of 1. The rectangle I use between x equals 1 and x equals 2 will have a height of f of 2. Between 2 and 3, I use the y value from x equals 3. Between 3 and 4, the height of my rectangle is f of 4. Why do I do the top right corner, not the top left? Because it doesn't make a difference. Here's the same function, same rectangles. Whether I do the right corner or I do the left corner, as long as I have enough rectangles, it doesn't really make a difference. Here's the right corner, here's the left corner. See how little difference it actually makes in my Riemann sum? So, for this video, I'm just always going to do the right corner. Let's see how this looks in a problem. In a problem, it'll say something like approximate this integral using a right Riemann approximation with two rectangles. Okay, so two rectangles. I'm finding this area. Oh, that was, just pretend I did that right. I'm finding this area, and with two rectangles means I'm going to do one rectangle. If I'm going 0 to 4, two rectangles means I need to go 0 to 2, and then 2 to 4. So one of my rectangles goes between 0 and 2, and because it's a right Riemann approximation, I make this rectangle have a height of f of 2. Its top right corner should line up with 2. And then I make a rectangle between 2 and 4, and its height will be whatever the y value from 4 is. So its height is going to be all the way up here. And that area I'm looking for, I'll approximate as the sum of these two areas. So this integral right here, I'm going to approximate as the sum of two different rectangles. One rectangle has a width of 2 and a height of f of 2. Let's just call f of x squared. It has a width of 2 and a height of 2 squared. Plus my other rectangle has a width of 2 and a height of 4 squared. I went from 2 to 4. I used the one on the right. I used the 4 to determine my y value. So it looks like my approximation for my area comes out to 2 times 4 plus 2 times 16, 8 plus 32. That's 40. This is my approximate answer to this. If I were to actually do fundamental theorem of calculus, the integral actually comes out to be equal to 21.3. So I'm close. I only have, what, like an 100% error or so? Not bad. There's been worse percent errors. In this one, I'm approximating square root of x, area under square root of x, between 1 and 10. And I want to do it with 3 rectangles. They don't have to be evenly spaced. Riemann sums don't have to be evenly spaced. I'm going to make it evenly spaced. Between 1 and 10, that's at 9 units. If I'm going to cover 9 units with 3 rectangles, each one has to be 3 units wide. So I'll go from 1 to 4, 4 to 7, and 7 to 10. And I've got some function, square root of x. Between 1 and 4, my rectangle goes up to a height of square root of 4. Between 4 and 7, my height is going to be square root of 7. And between 7 and 10, my height will be square root of 10. So my approximation will be one rectangle has a width of 3 and a height of square root of 4, plus my next rectangle has a width of 3 and a height of square root of 7, plus my last rectangle has a width of 3 and a height of square root of 10. I punched this into a calculator ahead of time so that I could tell you that this comes out to 23.424. That's my approximate answer to this integral. I also figured it out ahead of time what the actual answer should be. The actual answer should be 20.415. So I'm pretty close. Let's see. 3 out of 20 means I'm at like a 15% error. No one actually cares about percent error. I'm just sharing this to show not bad. 15%, still not great. It's not bad. But with more that was 3 rectangles. More rectangles, I could get much better. We'll do another. Oh, by the way, if I were doing this, I know each rectangle has the same width. So what I would have done is I would have done 3 times and just done all the heights. My height is square root of 4 plus square root of 7 plus square root of 10. I know it's the same thing, right? I just factored out a 3. But I would have skipped this step and just done this step. I'll let that digest. You can hit pause if you want to digest it. Okay, one more. Except 2 more. There is one after this. Approximate this integral 2 to 22 what random numbers of 1 over x using a right Riemann approximation with 5 rectangles. 5 rectangles this time. Okay, I'm going between, I'm not even drawing a graph. I'm just going to say I'm going between 2 and 22. I'm doing 5 rectangles, so I have a length of 20, covering that in 5 steps. 20 divided by 5 is 4. Each rectangle I need to go 4 steps forward. So I'm going to go 2 to 6, 6 to 10, 10 to 14, 14 to 18, and 18 to 22. And this is going to turn into a bunch of rectangles. My first rectangle is going to go up to whatever this point is. This point, I have some graph of 1 over x. And I line up all my rectangles so that their top right corner lines up. My rectangles are going to be, one has a width of 4 and a height of 1 over 6, right? My rectangle, my first rectangle, this is the point 6, 1 over 6, so it has a height of 1 over 6. My next rectangle has a width of 4 and a height of 1 over 10. And for the sake of space, I'm just going to factor out that 4 from everything. Right? My first rectangle has a 4 by 1 over 6. My next rectangle is 4 by 1 over 10. Then I have a rectangle that's 4 by 1 over 14. My fourth rectangle is 4 by 1 over 18. And my last rectangle is 4 by 1 over 22. If I distribute the 4 to each term, then I get each width times height. But it's easier if I just factor that width out from the beginning, since it's the same width for every rectangle. So my integral is going to come out to 4, carry the 3, 9. That sounds like it's going to be about 1.756. Did you like how I made noises as if I were doing math? I have a paper next to me. I did the math ahead of time. 1.756, and I also did the math for what the integral actually comes out to. If I actually do fundamental theorem of calculus and do ln of 22 minus ln of 2, it comes out to 2.398. That's actually not that good. That's like a 27% error. That's not great, but it's still, it's okay. I mean, what if I can't do the integral of something? Like if I were trying to do integral of sine x over x. There is no antiderivative to sine x over x. No matter how hard I try, I will not find an antiderivative. I can't do fundamental theorem of calculus, so this is a good way to do it. And although I had a 27% error, it would get better if I used more rectangles. And if I'm a computer, I can use as many rectangles as I want, or at least I can use a much larger number than 5. Okay, one more, and this time I really mean it. One more. Use the table of values to estimate this. So I don't even have a function this time. I'm just approximating this integral. In this integral, I'm going from 2 to 10, and I'm breaking it up into 4 rectangles. Width of 8, each rectangle, if there's 4 rectangles, has to have a width of 2. So I'm going to go 2 to 4, 4 to 6, 6 to 8, and 8 to 10. And each rectangle, because it's a right approximation, I'm going to use the value on the right. Between 2 and 4, I use the value of f of 4. This rectangle is 2 by f of 4 is 1. Then I do a rectangle between 4 and 6, and I use the value of f of 6 to determine that height. So it's actually negative in this one. Negative 2. 2 by negative 2. Then I do a rectangle between 6 and 8, and I use f of 8 to determine its height. This rectangle is 2 by f of 8 is 8. And then I do a rectangle between 8 and 10, and I use f of 10. I use the value from the right for a right Riemann approximation. F of 10 is 7. So this rectangle is 2 by 7. My approximation is going to be the width of all the rectangles times all their heights added up. Their heights are f of 4 plus f of plus f of 6 plus f of 8 plus f of 10. This comes out to 2 times 14. I get 28. That is my approximate value of that definite integral.